So using these integration techniques, we are still on working with integration by parts. And today's focus is going to be some special applications involving power reducing, larger polynomials, and also cyclic integration by parts where you need to use the process more than once. Okay, just to remind you that the basic expression for integration by parts is this expression here, that UdV, again, integration by parts, is being able to integrate a product of two functions, equals u times v minus v du. And also these guidelines here, just to refresh our memory, we're going to let dv be the more complicated portion, and we're going to let the u be the less complicated portion, but really the one where we can easily take the derivative and get a simpler expression. So just kind of keep that in mind as we go into these examples here. Application of integration by parts that we're going to go through is something called a circular solution, or I think I used the term cyclical solution, and that is where we have a product of two functions, and when you look at these two functions, whether you integrate them or differentiate them, if you do that enough times, you end up getting the same thing you started with. So they don't have powers that can be reduced. They don't have anything that can get more simple, so to speak. But it just ends up kind of staying within the realm of either sine or cosine and e to the x. And so in this situation, what we have to do is we have to go through the process enough times to get back what we started. So that's kind of the objective here, is to get back what we started with. And now the nice thing is, when you're talking about e to the x, you get back what you started with after the first cycle, whether you differentiate or integrate. With sine of x, so you can't get back to a sine of x unless you do it twice. You either integrate or differentiate once and you get cosine, and then you integrate and differentiate, or differentiate again and you get a sine back. So we know that we have to go through integration by parts 2 times to get the proper arrangement of terms back. And so in looking at this, since we really can't apply a theory of, well, how do you make one more simple as you do something to it? It doesn't really matter what you assign to what in this situation. So I'm just going to go ahead and let my u be my sine of x, and my dv be my e to the x dx. So when I integrate my dv, I get e to the x, and when I differentiate my u, I get cosine x dx. And I'm going to go ahead then and set up my integration by parts. So I've got kind of a reminder of what that is. So I'm going to take u times v. So u times v is e to the x sine x minus v du. So minus the integral of v du, it looks like e to the x cosine x. And so we don't get something that still we can integrate that easily, unfortunately, but we still have a product of two functions. So that being the case, we're going to go through the process again. And so I'm just going to kind of keep with this pattern. I'm going to let my u now be cosine x, and my dv be e to the x dx. So when I integrate, again, I get e to the x. Write that a little meter. When I integrate, I get v equals e to the x. There we go. And when I differentiate here, differentiating the cosine x, I get du equals minus sine x dx. And so when I put this together now in my expression, I go, and this really is just for this portion of the expression. So kind of keep that in mind. This has already been integrated and is out of the integrand, and so it is just e to the x sine x minus. Now we've got to apply integration by parts to just this portion of the integral. So my u times my v is going to be e to the x cosine x minus my v du. And if you notice, my v to u now looks like minus e to the x sine x dx. And so that looks like what we started with, except for this. And that's okay, because we can really easily pull that out of the integrand expression. So we have e to the x cosine x plus the integral e to the x sine x dx. For that portion of the answer. And now what happens is that I'm going to go ahead and get rid of the brackets here and rewrite this. So this equals e to the x sine x minus e to the x cosine x minus, distributing that minus sign, e to the x sine x dx. And what we do then is we set that equal to what the original problem was. And the original problem statement was e to the x sine x. So we were integrating e to the x sine x dx. So if you notice, we still have an integrand in the expression, but that's okay. We're just going to solve for that. So what we're going to do is we're going to add e to the x sine x to both sides. So just moving that to the other side, just like we would add opposites in any other algebraic expression. And so on this side, we end up with 2 of those expressions. And that equals e to the x sine x minus e to the x cosine x. So that ends up canceling out. And so if we divide each side by 2, we've just solved for e to the x sine, the integral of e to the x sine x, which is what the question was asking, is to solve for the integral of e to the x sine x. It just involved a little more algebra and one more IBP, or integration by parts step, than we were used to doing. And I know this is a definite integral, so we eventually have to plug in some upper and lower limits, but there is the expression for e to the x sine x, and we are evaluating from, get back up to the top of the problem here, 0 to 1. So if we're setting up that definite integral from 0 to 1, that means we have to evaluate that from 0 to 1. So we have e to the 0 sine, e to the 1 sine of 1 radian minus e to the 1 cosine of 1 radian all over 2 minus e to the 0 sine 0 minus e to the 0 cosine 0 all over 2. So evaluating and simplifying that gets us, let's see, sine of 1 and cosine of 1 radian, both are non-zero. So we're going to be looking at E sine of 1 radian minus cosine of 1 radian over 2 minus, and let's see here, this is 0 because sine of 0 is 0, but this is 1 and this is 1, so it looks like minus a negative 1/2. So simplifying a little bit and getting rid of some brackets, it looks like we have plus a half right there for the value of that integral. This variation, we can see that we have a polynomial expression x squared, so we can use the derivative to reduce the power, but we would have to use the derivative twice in order to get this power to completely disappear. And so that's the indication then that we're going to have to use integration by parts 2 times. And so when we're looking at this here, if we just kind of key into the power here, if that power is 3, we're going to have to use integration by parts 3 times. If it's 4, 4 times. So this becomes quite a lengthy process when you consider doing this process over and over. So, you know, this one, the general guidelines, I think, kind of holds true. Our u is going to be x squared, and our dv is going to be our e to the x dx, that more complicated expression. And then as we integrate, we get a v of just e to the x. And as we differentiate here, we get a du of 2x dx. And so as we put that into our expression for integration by parts, we have u times v. So that is x squared e to the x minus v du. And so v is e to the x, du is 2x dx. And so this again is a product of 2 functions, and I'm just going to simplify it a little bit. I'm going to bring out the 2 and rewrite it like this. So we still have the product of 2 functions, and so we still need integration by parts for that section of the problem. So we're going to repeat the process, just like we did in the earlier example. And whatever we get for the answer for the repeated process, we're going to put in here. So looking at that, we're just going to again follow with our same pattern here. Our u is going to be our polynomial x. Our dv is going to be e to the x dx. So when we integrate our dv, we're going to get e to the x. When we differentiate our du, our u, we're going to get a 1 dx, or just a dx. And so we'll go ahead, u times v is x e to the x minus v du. So v du is just e to the x dx. So you can see that the power of the polynomial has been reduced enough to be eliminated, and we no longer have a product of 2 functions in our integrand. So we can just go ahead and integrate this last portion here, and we end up with x squared e to the x minus 2x e to the x, and distributing the minus 2, we end up with a plus 2 e to the x for our expression. And this also is a definite integral from 0 to 1, so we are going to evaluate that from 0 to 1. Notice the pattern here. We've got our x, our polynomial, being reduced, and our e to the x that's staying the same, because no matter what you do to e to the x, it stays the same. And we're going to get into a way to do that a little more quickly in just a minute. Putting in our upper and lower bounds, we have 1 squared e to the first power minus 2 times e to the first power plus 2 times e to the first power minus, in parentheses here, putting in 0 gets us 0 there, gets us 0 here, plus 2e to the 0. And so we end up with, let's see, this is e minus 2e plus 2e minus 2, because e to the 0 is 1. So the value of this definite integral then is, these will cancel, e minus 2 would be the value of that integral. Now, if we look at this example, we would have to do integration by parts 4 times, which gets really time-consuming. And so there is a shortcut, which is kind of a nice thing, and the shortcut is called the tabular method. And the tabular method really is just kind of setting up a table and setting up a table and watching the derivatives and the expressions for the integrals. So we set up a table that kind of looks like this. We know our u is going to be our x to the 4th because we want to reduce that power. And our dv is going to be our e to the x dx. And then below that, we list the derivatives and the integrals of all the successive ones we need. So in other words, we differentiate this all the way down to 0. So we get 4x cubed, we get 12x squared, we get 24x, we get 24, and we get 0. And then we integrate this as many times as we need to fill in all these rows. So we integrate and get e to the x, and we integrate again and get e to the x, and again, and again, and again. Now let's undo that. Not sure what happened there. There we go. One last time. We get e to the x. There we go. Okay. So, so there's all our successive derivatives and integrals that we need, and then we just do a combination of terms. So we know that this first derivative goes with this integral, and then we have to do some, since we have an expression where it's u times v minus v, the integral v du. Since we have this minus sign here, that means we've got to switch signs every time we go through an integration by parts. We're going to have to take the opposite of that chunk at the end here. So we start out with a product here, and we'll keep that sign the same, and then, so we'll keep that sign the same. So for the same, I'm going to write a plus sign. So we'll keep that sign the same. And then this next product, we'll have to switch the sign. So I'll say that for taking the opposite sign. And then the next product, we keep the same sign, whatever it is. And for the next product, we take the opposite sign. Okay, and then we run out of products, so this isn't used and this isn't used, just like in integration by parts in general. So this answer looks like 4x cubed e to the x with the same sign, and it's positive, so it's going to stay positive. And then the next product is 12x squared e to the x, and this product is positive, and so we need to take the opposite of a positive, which is a negative. And then the next product is going to be 24x e to the x, and this product is positive, and we need to keep that same sign, so it's a plus. And then the next product is 24 e to the x. And this product is a positive product, and we need to take its opposite sign, which means we'd have a negative. And I'm just going to leave this as an anti-differentiation problem, so I'm just going to put plus c at the end there. Here's an application where we start out with a differential equation, and we have to apply the integration by parts skill to solve this differential expression. So if we kind of take this differential expression and write it in terms of dy dx instead of the y prime, you have something that looks like this. And go ahead and separate the variables. So we're going to divide each side by the square root of y. And we're going to re-express the differential dx on the opposite side so that we can get it into a differential sort of expression. And so when we rewrite this, we end up with dy over the square root of y equals, it should be a y, dy over the square root of y equals x cosine x dx. And although the left-hand side here doesn't require integration by parts, the right-hand side does. So what we're looking at is we're looking at integrating y to the minus half power x times cosine x dx. So let's go ahead and integrate each side here. And so integrating the left-hand side is going to give us, let's see, adding 1 to this gets us positive a half. Taking the reciprocal is 2, so this is 2y to the positive half equals, and then over here, we're going to have to decide what our u and our dv is going to be. And so we want to power reduce, so I'm going to put u equal to x and dv equal to cosine x dx. There we go. And so if we take the derivative of u, we get dx. And if we integrate the cosine of x, we should get this, excuse me, if you integrate the cosine of dv, you get sine of x. And so this side is going to be u times v, which is x sine x, minus v du. So this the sine x dx. And then so we've gotten rid of the product in the integrand. So we can go ahead and integrate sine of x, and sine of x is opposite cosine of x. And so we end up on the right-hand side with x sine x plus cosine x equals 2y to the half power. And if you're solving the differential equation, that means you're solving for y. So we're going to divide each side. You just need to clean this up now with a little bit of algebra. We'll divide each side by 2. So that's y to the half equals x sine x plus cosine x over 2. Then we have to square both sides. So we'll go ahead and square this side and square that side. And we end up with y equals x sine x plus cosine x over 2 with that whole quantity squared. Plus c. We can just tack on the constant of integration at the end, even though we integrated both sides. To wrap up integration by parts, here are some common integrals that you would run into. And so when we look at these things, we can kind of see that, you know, this sort of thing and these right here, I'll just circle them in red. These are definitely going to be power reducers, as well as these are going to be power reducers because we have that polynomial expression x to the n power. Okay, so all of these are going to be power reducers. So these are all our power reducers. If the power is bigger than 2, you might want to use that tabular method to save some time. And these down here, we've got our Euler's expression, e to the x, and we've got our trig expression, sines and cosines. And so these are definitely those circular or cyclical methods. So unfortunately, you're going to have to do integration by parts twice here. There's no way around it. There's no way around it. There's no table around it, since you have to kind of end up with what you started with and do some algebraic manipulation at the end.